Yes, so it's a pleasure to give a talk in a seminar dedicated to representation theory itself. So as Chris just said, I'm sitting here in quarantine, so I need to make a decision between giving a deep talk or giving a fun talk. I went for the fun talk, so let's see how it goes. So today's talk is about fusion rules for SL2, and this is all joint work with those three guys. This was really bad. Let me give it another shot. Very good. So Luis, Paul, and Giro. And we started this project during last year's trimester program in Bonn. And well, this is the outcome. I would like to tell you about what we know about SL2, or what we don't know about SL2, and what we know about whatever. Half of the talk, or let's say 40 minutes of the talk, is pretty much well known. As I said, I wanted to go with a fun talk. And a lot of people in the audience, I already spotted some, have contributed to many theorems I'm going to tell you about. So kind of the whole story for today will be that secretly, when you do this representation theory of reductive groups like SL2, toy case SL2 of course, what you're really doing in the modular case is you do some kind of fractal geometry. So you will see fractals all over the place. So let me just show you some of them. So throughout the talks, I would like to address three questions, and as I said, in all of them we will see fractals. And I hope to make it kind of enjoyable for everyone. So the questions I would like to ask, and I would like to think about SL2 being a toy case for something more general, so SL3 and beyond. My chair, for example, Chris has worked on SL3 and fusion rules for SL3 in the modular case. So I'm not saying nothing is known about those other cases, but for SL2 you can make kind of everything explicit, which is very nice. And I will start very slowly. I would try to explain, or will recall for you theorems which are scattered throughout the literature and usually very hard to find about, let's say, the object structure. So you think about having a certain category of modules, and what you really would like to study in the end is this last bullet point here. You would like to study them as categories, which is kind of the little bit the novel point of view. We'll see some nice diagrammatic studying those categories of modules. But I will start, as I said, with a more classical question like, what can you say about the object? Most of this is, as I said, well known, and most of this is a character computation. Some kind of, you want to write down your natural objects, and you would like to know their characters. That's kind of the standard question you ask here. A little bit more sophisticated, but still pretty classical, would be the question what you can say about tensoring of your objects. Because you have a Hopf algebra in the end, so you can tensor modules. You would like to ask, well, can I decompose tensor products? Can I write down the fusion rules? Can I write down some kind of object fusion rules? That's my second point. And in the remaining 20-15 minutes, we'll see how it goes. I will try to explain what is kind of really new. This philosophy which originated a long time ago, actually, but it took a while to really get started, is that you should actually study the categories as categories, meaning you should write down relations for morphisms between the representations instead of focusing on the object. And usually what people do in this setup is they like to write down diagrammatic presentations for those categories, and for those categories, as we will see, there will be the Temperley-Lieb TL category, which a lot of people have studied. It's one of those classical categories, diagram categories, attached to representation theoretical questions. So the only kind of technical point I need to mention here, because I will come back to that later, is that I would like to have an algebraically closed field. Characteristic can be anything, but I would like to be it algebraically closed because I really don't want to talk about the finite group. So what I don't want is something like SL2 over F5, for example, which would be a finite group, of course. So the finite group case, I will come back to that later, behaves slightly differently. Actually, not slightly different. It's really crucially different on a certain level from the case of the infinite group. So K is some algebraically closed field. I don't care too much about it. Just some algebraically closed field some characteristic, which I usually will be P in my notation. And P can be anything. It can be 2, 3, 5, 6. It can be infinite, which infinity, which is the same as P equals 0. You will see why I would like to think about P equals infinity as being P equals 0. But this is kind of the classical story that you see in modular representation theory. A really big prime corresponds in the end to characteristic 0. And what we will see are those guys here. So kind of classical fractals, in the sense that they have appeared in other forms of mathematics somewhere. So on the left-hand side you see some version of Pascal's triangle. We'll see that in a second again. And well, strictly speaking, I will only say that once, because I gave a very similar talk a while ago, and someone pointed out to me, wait, you're not doing fractal geometry, you're doing inverse fractal geometry. So what do I mean by that? So usually if you think about fractals, you have something that repeats if you zoom in on a smaller scale. Everything you see today is something that repeats if you zoom out and it will repeat itself on the larger scale. So in some sense I have inverse fractals. I'm probably not good enough and I will always just say fractals, but anyway. The whole point will be those nice fractal pictures that we will see. And kind of the takeaway message is exactly that you do this fractal geometry all the time. And what kind of distinguishes SL2 from everything else is that the fractals you see for SL2 are well-known fractals that kind of appear in other parts of mathematics. While for SL3 and beyond, you kind of hit kind of the border of knowledge and you really see new types of fractals turning up. So if you think about something like the Billiards Conjecture, which has become pretty famous, it's really a statement in discrete dynamics, which is the same as discrete dynamical systems are kind of the same as fractals. So it's kind of a statement about certain fractal structures. And you could actually restate the Billiards Conjecture instead of this dynamics picture. So the Billiards Conjecture is about certain characters for SL3. You can restate it in terms of fractals instead of this famous video Jordi made about this discrete dynamical systems. So the point is, I said again, everything you see if you do modular representation theory of those reductive groups is in some sense fractal geometry, which is kind of built in because if you're an expert, you know what a Frobenius twist is. So the Frobenius twist kind of builds in this inverse fractal structure. It scales everything up. But in my toy example, I don't need Frobenius twists at all. I can prove everything without ever using a Frobenius twist, which is kind of nice because I don't really know how it looks like in the diagrammatic setup that we will see later. Okay, so that's the setup. So let's get started. So let's get all on the same page. As I said, everything I'm telling you in the first 40 minutes is kind of well known. It's kind of folk theorems. But they are usually really hard to nail down or to find in the literature. So let me just be slow here. So I have this nice picture, which is Pascal's triangle. And what I'm writing down for you are the so-called Weil modules. Or strictly speaking, these are dual Weil modules. But anyway, which my notation is this funny delta symbol here. And they really go back, well, about 100 years. To Hermann Weil about 100 years ago. So he wrote them down, and this is really how he wrote them down. So for each natural number, I have those Weil modules, which are listed down, going all the way down here, and I have two numbers attached to them, which is their dimension, which is the number you see if you solve this equation here. So this is the dimension, the first number, which will be the really important number. That's why I like to write it as 5 minus 1, for example. And they have a highest weight, which is this number here, the power of y, and this is always one lower. So usually you would see something like people would write this as delta 4, and I like to write this as delta 5 minus 1, because the really crucial number will be 5. There's always this funny shift by 1. So the crucial number will always be 5. So just keep that in mind and don't be confused if you see whatever. Everything will kind of be a v minus 1 in my notation. And the reason is that I really care about v. I don't care about v minus 1. And you will see in a second why I really care about v. Anyway, So the Weyl modules are given by this nice picture, and these are the basis elements of the corresponding Weyl module. So this is the trivial module. It's one-dimensional. This is two-dimensional. That's a vector representation. This is three-dimensional, and so on. Four-dimensional, and so on. So they're really given by Pascal's triangle in a very, very strict sense, because this is the basis. And how does a matrix act? Well, a matrix acts just by the row expansions of the corresponding product here, and if you expand those products, you will see binomials. So this is really, really given by Pascal's triangle in the end. So Hermann Weyl wrote that down about 100 years ago, and what you can prove is that these are the simple modules of SL2, as long as you work over something like C or any other algebraically closed field of characteristic 0. And these are your simple modules. These are your simple objects of your category. So they form a completely non-redundant list of simple modules, indexed by natural numbers. Namely, my V here is my indexing set. Right? So this is just some natural number. Okay, but then Hermann Weyl also thought about finite characteristic. At least I'm pretty sure that Weyl thought about it, because the following is relatively easy to prove, and it's not so easy to track down in the literature. So, okay, so I just told you Pascal's triangle gives us the simple modules of SL2 in characteristic 0. So what about characteristic P? And the answer is Pascal's triangle in characteristic P. So Pascal's triangle modulo P gives us the simple modules of in the corresponding characteristic. So how does it work? Okay, so here's what Hermann Weyl did, or what I think he did. So let's say P is 5. Okay, so what you do is you write down those elements, and you write down this Pascal triangle, and you really think of this as having the corresponding entries in Pascal's triangle. So 0 over 0, you know how it works, right? Sorry, this was wrong. 1 over 0 in the next row, and 1 over 1, and so on. So really just Pascal's triangle. And you take those appearing binomials modulo 5, and you kill everything that is 0. So you mark it in a black color. I will zoom out in a second, then you will see the pattern immediately. And everything that remains is the corresponding simple hat of the delta module. So I have my delta module, which is just the whole Pascal's triangle. It's just the whole row. So this delta module and this delta module is just the whole row, right? It's always just the whole row. You write down Pascal's triangle, you write down the binomial coefficients, you get rid of the ones that are 0 in your specialization to P, and whatever remains, which is not 0, is the basis for the corresponding simple module of the delta module. In this case, it's a simple hat. And in this case, you can even read off, if you look at this row here, so this one is always a hat. So it's this 4-dimensional module here. This is my 7 minus 1 in my notation. And if you see here something remains, and you just look at the corresponding block of the same length, and it's an L 3 minus 1. So in this case, delta 7 minus 1 has the hat L 7 minus 1 and has another factor as 3 minus 1. And how does it look like if you zoom out? Well, it's exactly the picture from before. It's just the mod 5. It's just really Pascal's triangle mod 5. This is how it looks like if you only care what is 0 and what is non-zero. And these are really the simple modules, mod 5. So here, for example, is an unbroken east-west line, and this means the delta is the simple module. And right after it is a very small delta. So here is, for example, an unbroken east-west line, and right after it comes a very small delta, which is only supported on the 2 outermost points. And this just repeats itself in this very classical pattern of Pascal's triangle modulo 5, or modulo P in general. And if you now think of this little box here, roughly this one, is exactly the picture you see here. I just zoom out, and because it's a fractal, I can zoom out as much as I want. It always looks the same. Okay, and this little number here, this was really bad. Give me another shot, maybe black. So this little number here, the size of the first block, that is P. Size of the first block is 5. So if P is now very large, which is characteristic 0, then this little white triangle at the top is just everything, right? So if this is just everything, then all deltas are L modules, and you just recover what Hammond-Weil told us 100 years ago, the delta modules are the simple modules. And yes, so the statement here is if you do this trick in your favorite characteristic, 2, 3, 5, everything you want works, then you get also a complete list of a complete non-redundant list of simple modules, which is, I think, a very nice way to get the simple modules from Pascal's triangle. And let me also prove it for you, because it's not so hard. Okay, let me not really prove it. Let me just indicate how it works. So we are back to Pascal's triangle, and the calculation Hammond-Weil did was basically the following. So here's my Pascal's triangle, and as I said, you really need to look at those coefficients, and these coefficients will play a crucial role, and they are really given by binomial coefficients, because you just expand those products, and you look how often this term appears, and this is the action. This gives you the action matrix for this matrix ABCD. Okay, and this is really how it looks like. Don't look too much at the coefficients; it's not super important, but I just feed it into a machine. So, for example, if you have your delta 7 minus 1, you just, well, it's a 7-dimensional space, and you just write down the matrix, and in each row and column you just expand this and look how often the corresponding basis vectors appears. And one row should look very familiar. The first one, just look at the coefficients, don't look at the ABCs. Then you see, this is really bad, you see 1, you see 6, you see 15, you see 20, 15, 6, and this was a 6, and 1 again. And these are, of course, just the corresponding binomial coefficients, right? This is exactly the peak of the binomial coefficients. And in the other rows, they're just spread out binomial coefficients, if you want. So no wonder that there's a connection to Pascal's triangle. So nowadays, you wouldn't write this like this anymore. Nowadays, you would just say it's a symmetric power of the vector representations that correspond. But this is basically what Hammond-Weil would have done. And what you would then just check is that in this funny matrix, depending on ABCD, in this huge one, you never see a common eigensystem, which basically means that your module is simple. But if you go to finite characteristic, and that's what you would like to do in order to prove this theorem, you reduce those coefficients, let's say modulo 2, so here P is 2. And for example, this 20 up here would die, would be a 0. Here's a 10, they die, 0, and so on. Of course, I didn't do this by hand, I just asked the computer to do it, but it's really easy. And you can already see here that in the middle something funny happens, and there's a general pattern which looks very similar, just a bit more complicated, because I, of course, took the simplest example. And you can literally see that there's a common eigenvector, and if you have a common eigenvector, well, then you're dead in some sense, and you have found a submodule, or you're good, depends a bit what you want to do. But this is really how you prove it, and this is really, or this is how you could prove it. Nowadays you wouldn't prove it like this anymore, but this is how you could prove it. What I just said, this classification of simple modules given by rows and columns in the corresponding Pascal's triangle. And this is exactly then the statement. So this one is simple if and only if the corresponding binomials don't vanish. And there's a very, very nice, easy way to check when this happens. So if I write my v, remember I have always a v minus 1, and I would like to express it periodically. So the sum over the periodic digits. And this happens if and only if it's a prime power. That's what, or a multiple of a prime power. That's what I wrote down here. So it has only one non-zero digit. So it basically never happens. And if you think about it a little bit, these are exactly those cases where you hit an unbroken east-west line in Pascal's triangle. And the only thing you need to know to prove this is what is called the Luca Theorem, which is this very nice theorem how to express binomial coefficients in terms of the product of the binomials of their periodic extensions. So if you want to compute A over B, you ever wonder how to compute A over B, A choose B in characteristic P, you just expand A periodically, you just expand B periodically, and the corresponding a binomial is just a product of the binomial of the digits. And if you know that, you can just prove what I just told you. It's not so hard to see. Okay, I have a little box here, and I hope you don't read it too closely. That's why it's so small. But a lot of what I just said goes through in general. In particular, those while modules. It took a very long time to define them, but actually, so in general, I mean, but actually they are defined over the integers. So I was working here over a field, but actually they are defined integrally. So you can think of them as kind of an integral incarnation. And if you then specialize to your favorite field, they might be simple or not. They might fall apart or not. And an analog of this criterion, so I learned this, I should say this, not from Hermann Weyl. So he never writes this down as far as I'm aware, but I'm pretty sure that he knew about it. I learned it from Janssen's thesis, so where everything I just told you in the past 22 minutes is a small example in Janssen's thesis, something like a 3-line example. And if you extend that a little bit, you get the first 22 minutes of my talk. And Janssen actually does it more general, so he writes down for any general G, he writes down a root theoretical condition when the delta module is simple. Not, and that's a much harder question, not the decomposition factors of the delta module, but just when it's simple. So you can actually solve that problem in general. And for SL2, you can also solve the problem of the decomposition factors, which I'm going to explain next. So just for now, to wrap up, or to recall what we have just seen, so the simple modules are given by Pascal's triangle, whether you work in characteristic 0 or in characteristic P. It's the same idea. You take Pascal's triangle, you can read off the simple modules. And of course, you see a fractal because, well, Pascal's triangle mod P is the standard example of an inverse, of this inverse fractal. When you zoom out, you see everything repeated on a bigger scale. Okay. Before we can answer the question, or actually I won't really answer the question about the decomposition of the simples, so the how many, so basically this one, how many delta module, how many simples appear in a delta, because it's a kind of an ugly formula. There's a slightly nicer formula, which is obtained by, or it's related by some BGG reciprocity to the one, to this one here, which is a little bit easier to describe, and which I also will need later to explain the fusion rules, because the fusion rules are, as far as I'm aware, they're not so super nice for simple modules, but they are very nice for this nice family of modules which go back to Ringel and Donkin, and they're called tilting modules. And I won't define them. I don't really want to define them. For SL2, you can think of them, if you've never seen them, as the following. I will show you an explicit example in a second, but these are the indecomposable summons of tensor products of the vector representation. So the direct summons of this product, and the vector representation was the delta 2 minus 1 in my notation. This is, I admit, this is a fluke in SL2. In general, you would need a little bit more sophisticated definition. You would define them that they have certain nice, well-behaved flags. But for SL2, you can just think of them as being direct summons of tensor products of the vector representation. And in that sense, they really play the role of projective modules, because in general, if your characteristic is finite, I will come back to that later, my little reductive group SL2 doesn't have any finite dimensional projective modules, which is a bit of a pity. They kind of vanish to infinity, they get infinite dimensional. And the tilting modules play, in some sense, the replacement role for those simple modules, for those projective modules. And why are they called tilting modules? Well, I not really defined them, but basically they have this delta and nabla filtration, and they have this nice property. If you just tilt your head so that you have a delta filtration going upwards and you have a nabla filtration going downwards in this picture, and if you tilt your head, you see exactly the same picture, not just because delta tilts to nabla, but also because exactly the same. So if here's a v minus 1, then here's a v minus 1. If here would be whatever, this is y minus 1, that you would see here y minus 1. So if you know a delta filtration, you know a nabla filtration. Tilting modules, you tilt your head, and or you tilt the module, whatever you prefer, and you see exactly the same thing. So they really kind of, actually, I should have said, they play the role of projective injective modules in some sense. So they have this nice duality symmetry. And kind of the point is why you might not have seen them if you usually doing some kind of generic representation theory over characteristics or characteristic 0, let's say over the complex numbers. There's this really general theorem. If a tilting module happens to be its hat delta module, so the top delta module you see, so this one here, my little triangle at the top, then actually it's also the simple module and actually also the delta module. All of them are the same. And this is what happens in the semi-simple case. So in the semi-simple case, all tilting modules are delta modules, all delta modules are those nabla modules, which are the dual delta modules. All delta modules are simple, and all categories of potential modules just coincide, and they're all the same. But in general, they're not. The tilting module is big, the delta module is in between, it's kind of a standard module, and the simple module is small. That's how you should think about them. A little bit more in some concrete pictures. So here's an example of how such a tilting module looks like. This is the 4-1 tilting module. So it's built out of a 4-dimensional delta. Remember, this was the dimension of my delta. It's up here, and it's in the cyclic pattern. It has a nabla at the bottom, and it's really like a cycle diagram. It's certainly bigger than both the delta and the nabla. And I also indicated what happens in characteristic 3. So in characteristic 3, so I kind of indicate what happens. So this is really the picture for the Lie group. For T4-1 in characteristic 3, the difference doesn't matter. But anyway, so these are the standard generators that you usually see acting here, let's say, for the Lie group, F and E. And as you can see, some of them just die. So this 3 here will die. So you can't hop out of this little box here anymore. And that's then a submodule sitting in the delta 4 module, which was well, I have only a picture for characteristic 5, but it would be this little submodule here sitting in the delta module. And the corresponding quotient in the delta module is this one here. So this is the L4-1, and it sits as a submodule in the delta, in the nabla, because here the arrow goes the other way around. So this arrow is the 0 arrow, it goes the other way around. So as soon as you're in here, you're stuck and you have the submodule, and this is the quotient. So everything turns around. And T itself is then built out of the delta and the nabla module in exactly this fashion. So the T is the big one, it contains everything. The delta is the integral one, it's in the middle, and the simple is a simple one, it's a small one, it can't get any smaller. Okay, and you also see this nice symmetry, this tilt your head symmetry, and it basically looks the same. Okay, this was the tilting modules, and the natural question you would then ask is, well, how many simple modules appear in the tilting module? The better question to ask is how many Weil modules appear in the tilting module. And the answer is again given by Luca Theorem, and I'm going to explain that in my example down here. So as soon as you understand this example, you can do it in general. It's given by the so-called digit game. It works as follows. You write down your number. Remember, this is my V. Right? Everything is V minus 1, so this is my V. And let's say I'm working in characteristic 11, and this is almost the biggest number I ever wrote down on any slide. But it doesn't really matter. What you do is you express this periodically, and this is how it looks like. And you basically look at the vanishing, the maximal vanishing obtained if you look at the binomial, and you know how this looks like by the Luca theorem. You would count 4 zeros at the end, so this vanishes of order 4. So and this means this guy has 2 to the 4 Weil factors. So the number of Weil factors is always a power of 2. And the power of 2 is given by the vanishing of the V binomial given by the Luca theorem. And it's really just what I just told you 10 minutes ago, how to look at those matrices. You just need to be a little bit smarter to really pick out the different summons. And what you do is you kind of kill them step by step by looking at the periodic evaluation of those binomial coefficients, and then you kind of in each step you collect the corresponding either delta or simple modules, depending a little bit what you want to do. A little bit easier to remember, or the same actually, is you can really write down the Weil factors. So you can answer this question: what is T over delta for various inputs, like this one has input V, this one has input W, and it works as follows. You just write down V again, so you always write down V periodically, so AR up to A0, and you allow yourself to just invert some of the coefficients. I call it the negative digit game, so you can flip the signs of all those coefficients except the leading one, because if you would flip the sign of the leading one, you would get a negative term, and you just naively interpret this as a natural number by just taking exactly the same sum as before. Just now some of the things might be positive or negative. P to the I, 1 over all I, and whatever number you see, that's the Weil module that appears in your decomposition. And if you think about it a little bit, this is just the same as picking a sign for all of those. And how many do you have of those? Well, you have, let's say V has a certain number of non-zero digits down here, and then you have 2 to the number of non-zero digits, which was exactly the number of Weil factors from before. So here I do an example, exactly the same example from before. So you expand this thing periodically, and of course the computer can do that. It's very easy, or you can do it by hand if you want. And you just take all the different sign combinations, not touching the first digit, and whatever comes out, for example, this one here would be then a Weil factor. And part of the theorem, which I always forget to mention, I don't really know why. Part of the theorem is actually also that this is multiplicity free. So either a delta appears or it doesn't. And this negative digit game tells you whether it appears or not. Right? It's a 0 or 1 question. I always forget to mention the multiplicities. Anyway, and if you write down the matrix, the Catalan matrix, so exactly the corresponding question, you see again one of those well-known fractals. So it's this thing that repeats itself always on a smaller scale, something like this, all the way up to infinity. And of course, the length of those small segments here is 3, the length of the bigger segments is 9, the length of the even bigger segments is 27. So this is characteristic 3, as you probably already guessed. The length of the next segment is 81, I guess. So the next prime power, whatever. And you see this nice pattern of, again, a fractal, or an inverse fractal. So if you zoom out, it looks exactly the same. And yes, from this inverse fractal, so there's kind of standard philosophy. If you know those multiplicities, you by some kind of BGG reciprocity also know those multiplicities. And you can actually also write them down. It's just tilted to the side. It's the same picture tilted to the side. So those are the simple multiplicities. So this is delta over L. So it's kind of a little bit of flawed BGG reciprocity. It's not quite BGG. And this is also why those numbers are a little bit harder to write down, because you kind of, we did that, by the way, so there is an explicit way to do this in the paper, so we wrote it down. I don't claim this is original. I never seen it before, but certainly someone knew that before. It's an explicit formula, but it's just much harder than this picture, because this picture is kind of built just the way it is, and for the other one I only know a recursive formula, because it kind of tilts this strange way to the side. So you kind of need to know a little bit what is happening upstairs, so that you can really determine what's going on in your local picture here. So in some sense, the delta over L is a bit trickier than the T over delta. So this is T over delta. So here I just told you the negative digit game, and here is kind of a recursive formula, which I don't even want to write down in this talk. It's not so bad, but it's certainly not as nice as just looking at the periodic extension and flip some sides. Okay, so this was a classical story. Let me repeat what I just said, and then let us go on. Simple modules, tilting modules, characters, character formulas. I should have said that if you know those delta over L, you can also write down, because the delta characters are just the classical Weil characters. If you know delta over L or T over L, you can actually write down tilting characters or the simple characters. Anyway, so what I just explained is that both of them are given by fractals, by kind of classical fractals related to Pascal's triangle, modulo p. So if you're like me and you like just to play around with little pictures, then you might wonder, can you push this idea further? And the answer is yes, you can. Again, in this part, so I haven't seen those rules that I'm going to show you, but I'm pretty sure someone knows them, so I would be happy to have some references, someone knows references. But what I'm basically trying to address is, can we write down the fusion rules, right? So can I decompose tensor products of tilting modules into tilting modules using some version of fractal geometry, some fractals, well, maybe I shouldn't call it fractal geometry, some discrete fractals related to Pascal's triangle in the end. So what I'm going to explain first is how to do that, and then I will briefly explain how the tensor ideals look like, which is kind of a direct corollary of what I'm going to explain first. So the tensor ideals are, of course, again, well known for ages, and it's really a weaker. So writing down the structure constants is a stronger statement than writing down the tensor ideals, the thick tensor ideals. I'm going to explain what all that means, so don't worry. I sadly don't have an answer in general, so I don't know how those coefficients look like in a very nice way. If someone knows, I would be very happy to know. Yeah. So let's get started. So I would like to solve the problem of tensoring with T1. And this is now very bad notation. I should have said tensoring with T minus 1. T2 minus 1, which is equivalent to my vector representation. So for lovers of the Temperley-Lieb algebra, I would like to understand the what is called the Grothendieck ring of the Temperley-Lieb algebra, if you want, of the Temperley-Lieb category, if you want. Okay, and I will explain the answer in a graph because that's kind of the easiest way to do it. And just to get us all on the same page, I would like to write down a fusion graph, which is what people in finite group theory do all the time. So it works as follows. You take your favorite module, dv minus 1, and it acts by tensoring on your category. Okay? And since you're acting on a category, everything is given by natural numbers. So this guy actually has an action matrix given by some natural entries, natural number entries. If you whatever 2, 2, 3. Well, this is bad because it's actually a symmetric matrix in this case. But anyway, something like that. Because you can just, well, you tensor your module, and tilting modules form a monoidal category. So the indecomposable tilting modules form a basis. Tensor your modules together, expand it in the basis. You see natural numbers because you're working the category. Write them in a matrix. That's a graph, because every integral matrix is actually a graph. Very easily given. Let's say 2, 3, 2, 2 would be the graph given by two vertices, just in, well, let's say 1 and 2, 1 and 2, and you would write down, let's say 3 edges from 1 to 2, because this number here is 3, and in this case, because it's symmetric, so maybe it wasn't a very good example, but anyway, you would also write down 3 edges from 2 to 1, and on the diagonal you would see loops, so 2 loops here and 2 loops here. And you can write down a graph associated to an object in your category, which is called the fusion graph. And the point is, the fusion graph, if you believe in this philosophy of having fractals, then the fusion graph should be a fractal graph. And indeed it is. For everything I ever tested, you can easily test this using a computer, of course, you see fractal graphs, and then it's kind of a matter of writing it down, well, not just using a computer, but writing down a proof that what you actually see is true. And I can only do this really for this T1 case. And in the T1 case, this is how it looks like. So I like to illustrate it on a circle. And what you see here is characteristic 3 versus characteristic 0. So let's discuss characteristic 0 first. So I told you that my delta modules, no, I haven't told you actually, the delta modules have the same indexing set as the T modules have the same indexing set as the L modules. It's always the natural numbers. I haven't told you that. I hope it was on some of the slides. So this is my indexing set for my matrix that I'm going to write down. It's an infinite matrix, and I cutted it off at, what is it, 25. Right? I just cut it off at 25, so I only illustrate the first 25. And I never found a really canonical way of doing it, so I like to do it on a circle. And in this case, it works as follows. I have a 0 here, I have a 1 here, I have a 2 here, a 3 here, and so on. And it's very easy tensoring. This is tensoring with T1, which is just a vector representation. And the tensor rule for the vector representation is the same as the multiplication by quantum 2, because quantum 2 is a parity operator representation. And this is as follows. You always have an edge going upwards, and you always have an edge going downwards. It's a very boring fractal. It's not fractal at all. So it goes all the way just down the sheet on line. But I like to illustrate it in a circle because this one is not so easy to do it on line. It's very, very simple. It just goes in an infinite circle. The infinite circle wants to close out and point to the infinity. So here's my point. And do the same thing for the other one, and you see this funny pattern. You always have the upwards going edge, so it's always the same, so you always go upwards. And the downwards going edges are the interesting ones. So that just means if you tensor, I write out the difference formula in a second. But anyway, it just means if you tensor this C1, you always get the next one, the one you would expect, but you might jump down very far. You might jump down very far, because a lot of those jumping down edges here. So here's an edge that jumps you from 25 down to 8. And this means if you tensor T24 with T1, then actually in the decomposition you see a lot of things, in particular you see T8 here. This is how the graph looks like. The pattern is as follows. It's always, as I get, only the downwards pointing edges are inverted. The upwards pointing edges are always 1, 1, 1, 1, 1, 1, 1. Same as on this side. And the downwards pointing edges have the following characteristic P behavior. So they go a missing edge, which is a zero label edge. And just illustrate it to make feel what the parallelicity here is. Then you have the two label edge, which is a double edge. The two label edge means the sum of it is twice. And then you have a bunch of one label edges, such that this whole tail here is of length P minus 1. B, not P minus 1. So in this case, it's 0, 2, 1, 0, 2, 1, 0, 2, 1, 0, 2, 1. In characteristic 5, it would be 0, 2, 1, 1, 1, 0, 2, 1, 1, 1, and so on. This is, now you might complain, wait, that's periodic, that's not a fractal, that's periodic. Yes, that's right. And the point is this pattern now repeats scale up by P. So you get longer edges jumping down, so the small edges jump down P to 0. The long edges will jump down P steps. The longer edges will jump down P square steps, and so on. And they satisfy the same periodicity. It's 1, 0, 2, 1, 0, 2, 1, 0, 2, 1, 0, 2, and so on. Until you get the next square power when you see the longer edge, and it does exactly the same thing. 1, 0, 2, 1, 0, 2. Or in general then, whatever. 0, 2, 1, 1, 1, 1, 1, 1, 1, 0, 2, and so on. So it's really a fractal graph. You zoom out, it looks exactly the same. And if you like Portelli diagrams, you basically can't see this Portelli diagram. So let me instead zoom in a little bit. Give me a second. Zoom the Portelli diagram. Okay. Because it's very hard to put it on the slide. So you might have to think in terms of Portelli diagrams instead of in terms of Hilton graph. This is what it looks like. So it's the usual Portelli diagram we would like to write down. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Next one 0, 1, 2, 4, 5, 6, 7, 8, and so on. And the usual Portelli diagram will just look like this. It's always just splitting, just pay out edges. And now we have to find periodicity. So the dotted edge is 0 edge, the green edge is double edge, and you get 0. This is again characteristic 3. No edge, 1 edge, 0 edge, double edge. 1 edge, 0 edge, double edge. 1 edge, 0 edge, double edge. And roughly each prime power, and we'll see the lower edge is turning up. 1 edge, range fitting in, and so on. Example too fast, have a look at the paper, because it took me a while to illustrate this, see the back of it. Anyway, the point is, it's again a fractal. Everything is a fractal. And here's a rule if you like to write on the formula, you can write on the explicit formula. Okay, that's not very much more than explicit formula. The proof strategy, let me tell you what the first strategy is. Well, you take the combinator machine knows the characters, and tilting models, if you know the model is tilting, are determined by the characters in this case. So you just use the combinator machine, it's a character computation, that's the formula, and you prove it. Not too bad, actually. The proof itself is really simple. It's surprisingly simple if you know what to do. It's whatever, five-line combination of Swiss characters. It's not so bad. Again, I suspect that someone has done this before, but I kind of never saw it. Usually people stop roughly around the fundamental algorithm, because that's kind of where the fractal structure kicks in. So it kind of describes the periodicity, but not the fractal structure. But I need to stress this again, I'm not claiming originality, I'm pretty sure that someone has done this before. What I'm also pretty sure is that no one has ever categorified this, and that's where I'm going next. But let me just briefly discuss the tensor ideals, because they also have a fractal structure, and it's very easy if you just look at the graph. It's the strongly connected components of that graph, and strongly connected is just in the oriented sense. So this is not a strongly connected graph, because I can't go away from this edge anymore. In particular, because of this funny zero edges, I'm stuck here. So this thing corresponds to a tensor ideal. Strictly speaking, it corresponds to a quotient of a tensor ideal. But anyway, it's kind of the starting point of a tensor ideal. And in each prime power, you see a next slice because of those missing edges. And the long edges jump you exactly to the beginning of the tensor ideal. Exactly down to the beginning of the tensor ideal. And the statement then is that every tensor ideal, and with a tensor ideal, so when I write this funny symbol tensor, then it's actually, strictly speaking, an ideal defined on morphisms, but the statement is I don't need to worry about morphisms. Every tensor ideal in this case is thick, which is the same as you define it on objects and takes the identities on those objects as generators for your ideal, which is a much stronger condition than just having some random ideal in a category given by morphisms. But in this case, you don't need to worry about the difference, because they're just the same anyway. And they are given by prime powers in exactly this fashion. So again, a very easy to remember statement. Tensor ideals for SL2 are given by prime powers. And if you wonder now what is the case p equals 0, well, you only have one tensor ideal, because the first prime power is already p is equal to infinity, is already somewhere very far out at infinity. Yeah, and why don't we have projective modules? Well, here's the proof that we don't have projective modules. Projective modules, at least not if the characteristic is finite, because projective modules would form the maximal ideal in this chain. And there is just no maximal ideal, it's an infinite chain. So projective modules vanish to infinity. Basically, why do projective modules form a nice ideal? Because projective tensor anything is projective. Projectives are kind of like big idempotents. Whatever you throw at them, they spit out projective modules. Anyway, this is a proof that you don't have any projectives. There's of course an easier proof than writing down the tensor ideals, but this is a particular proof that there are no projective modules. But you still have tilting modules. As I said, you have tilting modules for any composable tilting modules indexed by natural numbers. Okay, and then you can play some tricks with it. You can write down several quotients with infinite chain of ideals. You can take infinite chain of quotients, and they are called the Valinde categories, the prime power Valinde categories. People like Ettinghoff, Ostrich, and Benson like to study them a lot recently. They turn up as funny, nice examples in some kind of characteristic P analog of Tanakian theory. But anyway, I'm not going to talk about that anyway. It was just an information for the experts, which are probably in your audience anyway. And well, what I would like to do is I would like to write down the Catalan matrix of this finite. This is now a finite category because you kill this infinite cell. let's say you kill this part because you take the quotient, so everything that goes to infinity, you kill it, and you only have this small remaining part here, and this is the Valinde category, or these are the these correspond to the simple or projective objects in the Valinde category. So you can write down the Catalan matrix, and this is how it looks like. It's again a fractal. It's this arrow in an arrow pattern, and the colors indicate multiplicities. So here you see multiplicities, and again the colors are also fractal, so the multiplicities are also in a fractal pattern. Anyway, details, I don't want to talk about Valinde too much because I'm running out of time, but you can find some details in the, actually not just in our paper, but also in the Benson Ettinghoff Ostrich paper, which I forgot how it's called, but I think they only have one paper together. So it's Benson, Ettinghoff, and Ostrich. Okay, so up to this point, I'm pretty sure everything I just told you was well known. Maybe very, very hard to track in the literature. Maybe my exposition is new, whatever, but it was certainly well known. So let's address the last question that I had, namely, can we study everything in terms of category? So can we study, well, let's say SL2 mod, or maybe it's analog SL2 tilt as a category? So both of them are nice tensor categories. You want to study them as monoidal categories. And the main idea that kicks in here is the Temperley calculus. And just as a reminder, it works as follows. If you don't get the details, it doesn't matter so much. It's this diagram calculus, and it's extremely easy to define. It is just one generator, which in my notation is just a dot, basically, which I don't draw anymore. So this goes from 3 dots at the bottom to 1 dot at the top. And it has just 2 generators, which are cups and gaps. And it has just 2 relations. So a cup goes from 2 dots. Ah, this is bad. This is exactly the opposite of the convention. So so the cup should go from 2 dots, 2 bullets, to 0 bullets, and 0 bullets is my monoidal unit. So this is nonsense here. Typo. Very good that I can correct my own typos live. Anyway, so you have only 2 generators, and you have only 2 relations. Topological relations. You can remove a circle with a cost of -2, and you have the zigzag type of relation. And if you like Deligne categories, that you can think of this as being a Deligne category by replacing this by kind of formal variable, and you can think of this as a Deligne category associated to this one, actually, as I will show you in a second. But anyway, you can write down those nice diagrams using some conventions what crossings are, and then you just write down your crossing diagrams. Very nice diagrammatic description of the category, and the theorem is, of course, which is, I think, the Folk theorem. Never saw it anywhere written down, but basically it's tilt is the kind of, so TL Temperley is an integral model. It's defined integrally of the category of tilting modules. That is, if you fix your favorite field, you get an equivalent of categories upon throwing in the usual words like additive and idempotent completion. So you can think of this as an integral module. You can think of this as playing around with the delta parameter, so instead of having -2, for example. And several people did that. So very recently, Robert Spencer and Stuart Martin, for example, played around a little bit with this category in basically integral, even in some more fancy setup like in mixed characters. But anyway, so this is really kind of this integral model of the tilting modules. And if you're like me, then you would start now playing around with those diagrams. And that's exactly what I'm going at in the last 5 minutes. So now you have a diagram presentation. You play around with those diagrams. And yes, you can write down a quiver associated to tilting modules. And you can study relations among morphisms and so on. But for the last 5 minutes, I just want to explain what to do with the fusion rules in this case. And let me just add here that this theorem is wrong. Okay, it's wrong, it doesn't work if k is finite. Okay, so this is the point where it falls apart. So this doesn't work if k is finite. This is based on Chauval duality, and Chauval duality fails for a finite field, when my SL2 would be a finite group. That's why I don't want a finite group, because this theorem is false. And to give you some hint why this is supposed to be false, is if you look at how this is defined, you objects are tensor products of this T1 representation, the T2 minus 1. And in each step, you usually pick up a new factor, the new highest weight module. And the finite group has only finite amount of information. So at one point, you don't pick up a new module anymore, but the new one, the apparently new one, actually is one of the old ones. And then you get bigger home spaces. So this side actually explodes for the finite. The analog of this side actually explodes for the finite group. So the temporally deep algebra is too small. There is no surjection anymore. Left side, there is also a kernel. So this just doesn't work anymore. But I'm ignoring the finite group, so let me ignore the finite group. So what then people did is, well, under this bijection, you can think of what are the idempotents in your category. And I should have named here also Stuart Martin and Robert Spencer, because they also worked on this. But for characteristic P, this goes back to those three guys. I'm not going to explain those morphisms. I just put a box here. So I have a purple box, which are those idempotent morphisms, and I will take the purple box as a black box. So I'm not going to. It's an idempotent, right? An idempotent in any reasonable category is some crazy linear combination. What I only care about are the properties of those idempotents. And the main property is that under this equivalence, it's sent to the corresponding tilting module. So the corresponding explicitly idempotent in this n space is this funny box here. And they are called P. Jones-Wenzel projectors, in analogy to the Jones-Wenzel projectors in characteristic 0. Okay, so black box, which is purple, it's an idempotent. And the question I would like to address in the remaining 2 minutes is, can we categorify the tensor product rule that I just showed to you, the one that lives on this circle or on this funny fractal Bertelli diagram? And the answer is, well, I wouldn't give this talk if the answer would be, I don't know what to do. Actually, we can. I just don't have too much time anymore to explain it. The only thing, so if you've never seen temporally deep algebras before, I'm pretty sure you can't follow anymore. Bear with me, it's only 2 more minutes to go. So basically, this is a generic rule. It's multiplication by quantum 2. So this is quantum 2, if you want to think about the quantum 2. That's a character, and this is how it looks like. You always go one up and one down. It was in my graph, they're going up and down edge. And it's categorified by the usual Jones-Wenzel rule. So the white boxes are the classical Jones-Wenzel projectors over C. And it's just really categorified by this rule. Here we have V minus 1, here we have 1, here we have V, and here in the middle you see V minus 2. And you only care for the middle slice. And yes, we can do the same in characteristic P with the purple projectors. It looks very similar, but you for example, I just give you an example how it looks like. You see a nilpotent error term turning up. So it's almost the same rule, but you're in a non-semi-simple case. You should expect nilpotent endomorphisms turning up. This is almost my last slide, so I'm almost done. And the statement is, yes, we can. Yes, we can. So we can categorify the funny rule here. It looks exactly the same. You write down explicit idempotents. And I'm going to explain in a second. That's the last thing I'm going to tell you, that also those idempotents are defined using a fractal pattern, of course. So what is the difference to the one before? Well, you still feed the problem into a machine. There's a computer program which can calculate with those idempotents. You guess the formula, and then, well, you try to come up with a strategy to prove it, because it's not so easy as far as I know. So we have a huge inductive argument in the paper. I don't know any. Well, it's something like a 10-page tandem type of inductive argument. A bit complicated. So much harder than the character computation for this formula here. Wow, this was really bad for this formula here. Anyway, so this is the last pattern, the last slide. So even those idempotents are given in a fractal form. So you should basically think how it works is you take your temporal leap diagrams, the usual recursion, and you scale everything by a factor of p. That's the secret, the implicit Frobenius twist that happens here. You write down new idempotents, and those are the ones you will take for the corresponding formula. Anyway, I'm 1 minute over time. I hope you apologize, and thank you very much for listening.